All right. So we're starting now. How is the Monday evening going? Hope it's chilled. All right. So we are going to be doing continuing with rustlings. Yep, like we always do. And I think we left off. We took care of the chapter on, I think it was generics. I think it was here. Yep, on generics. Just turning down the music a lot. Yeah, we took out a chapter on about traits. Yeah, so we fixed all the exercises there, and the next was supposed to be quiz. So it's like the quizzes. So let's go there. It's quiz 3. Quizzes. So quiz 3. There's already a quiz 3 program. Well, interesting. Let's try to solve this one. What does it say here? So the quiz test generics and traits. An imaginary magical school has a new report card generation system written in Rust. Currently, the system only supports creating report cards where the student's grade is represented numerically, e.g. 1.0, 5.5. However, okay, it's represented numerically, so I guess 1.0, okay. However, the school also issues alphabetical grades, A+ to F-, and needs to be able to print both types of report card. Make necessary code changes in the struct report card, and the implementation block supports alphabetical report cards in addition to numerical ones. All right, so we have the report card struct. It has the grade, student name, and student age. We have an implementation for report card. It has a print method which just prints the student's name, achieved a grade of wait, sorry, so it will be, I mean, this first value we printed here, so that'll be student name, in brackets student age, achieved a grade of grade, okay, and it only prints, I guess we create a report card, and right now it only supports a numeric type. Actually, it only supports, yeah, student's grade can only be represented numerically. Yeah. So we need to make this generic, right? So the test here, as you can, so we have a report card. The grade is 2.1, and here this is the problem here. So we have a grade that should be A+, so like a string. So let's change this. We need to define a generic parameter, and this will no longer be the grade, no longer be F32 type. It should be that type. Yep. And now we need to also define the generic type here and say it's over the generic type here. Mhm. So with this, yep. So now we have the problem that we are not able to yeah, so we need to restrict the type with display and say that this implementation think is that where it's supposed to be? Associated item considered not allowed here. Also, it shouldn't be here, right? I mean, I'm not sure where that. I'm not sure where that should be, but I know we can restrict that. Is it here? Okay, it's here. Yeah, this is where we define it. Okay. So now we are able to do this for report card that over the generic that has the concrete type F64 or whatever it is, and string slice. All right. Okay. So yeah, this is done. The next one about lifetime. And now we go to the chapter on lifetimes, or the exercise on lifetimes, which I believe we've done, but let's see. $16 on lifetimes. So I think we actually took care of lifetimes. I think, okay, this is lifetime zeros by example. I think it's a different, I'm just gonna move that to here. Probably here is best place. Wait, no. Yep. Okay. So yep. A lifetime. By the way, this book is what is. Yeah, I think this is the one we're using. So yeah, a lifetime is a construct the compiler, or more specifically, its borrow checker uses to ensure all borrows are valid. Yeah, I think we. Yeah, okay. This is a different one from the Rust book, but yeah, same concept. Take for example the case where we borrow a variable via this. The borrower has a lifetime that is determined by where it is declared. The borrower is valid as long as it ends before the lender is destroyed. However, the scope of the borrower is determined by where the reference is used. Okay. Lifetimes are instead below with lines denoting the creation and destruction of a variable. I has the longest lifetime because its scope is entirely, and because its scope entirely encloses both borrow 1 borrow 2. You should have borrow 1 compared to borrow 2 is relevant since they're disjoint. So we have this main function here. I is 3, so lifetime for I starts here. And then we have this block. So lifetime for I start here and lifetime for I ends here. Okay. Now we borrow. So borrow 1, lifetime starts here. Okay. And borrow 1 ends here. Borrow 2 here and ends here. Note that no names or types are assigned to label lifetimes. What do you mean by no names or types are associated to label lifetimes? Well, I guess we see that. So the explicit annotation. ReportCard uses explicit lifetime annotations to determine how long references should be valid. In case where the lifetimes are not deleted. We looked at lifetime edition on Saturday, I think. ReportCard has explicit annotations to determine what the lifetime of a reference should be. So this is the explicit annotation for using the lifetime. The apostrophe and the lifetime parameter. So foo has a lifetime parameter, lifetime A. Similar to closures, using lifetime requires generics. Additionally, this lifetime syntax indicates that the lifetime of foo may not exceed that of lifetime A. Okay. Explicit annotation of a type has the form borrow or reference, lifetime, and the type, where a lifetime here has already been introduced. In cases with multiple lifetime, the syntax is similar, like so. So foo has lifetime parameters, lifetime A and lifetime B. In this case, the lifetime of foo cannot exceed that of either A or B. Okay. So we have print refs that takes 2 references to I32 types, which have different lifetimes, A and B. These 2 lifetimes must be at least as long as the function printf. But in this case, there is no return from here, so this is not relevant. Why would this be necessary? I think I don't want this. Oh, is that? Okay, here. So I'm saying if we don't have these lifetime parameters specification, we shouldn't have a problem. Apart from even the elision, yeah, I mean, apart from the elision, we don't have any return type as a reference, right? So shouldn't matter. But anyway, that's on the side. a function which takes no arguments but has a lifetime parameter. Actually, this example is just showing how to introduce lifetimes or lifetime parameters. So a function which takes no arguments but has a lifetime parameter, lifetime a, and no arguments. Okay. So you have x here, which comes to scope here. And then you have that y, which is of, you're attempting to give it the lifetime a of type I32, and you're giving it a reference to x. Why does it fail? Attempting to use the lifetime a as an explicit type annotation. Inside the function we fail because the lifetime of x is shorter than that of y. Why is it shorter? Yeah, okay. Yeah. Yeah, it has moved, right? That's it. Let's see. It's called field bar or something like that. I want to write this without I want to just see. So we had a let x be, was it 12? I guess it was a, yeah, 12. And so wait, what if I say mismatch types? I mean, for integer types, it's not moved, so we're fine. So there's no issue here. It doesn't get moved. So, but what you're trying to do here is trying to assign the lifetime a. But the lifetime for, I mean, normally, Okay, so oh yeah, y has a longer lifetime. Yes, based on this that you're assigning here. But then what is the lifetime of x here? This doesn't make sense. Why? I would expect normally that x is valid up to this point. So let's see. So this is where we ask Claude about it. So my question will be why? Okay, so the key insight is a lifetime A is not the lifetime of the function body. It is a lifetime parameter chosen by the caller of field borrow. So when you write lifetime A in the function signature, you're saying the caller gets to pick a lifetime A, and it can be any lifetime they want, including one that outlives this function call, right? This function has to be valid for every possible choice of lifetime A. So what happens inside? This is a local variable. All right, now it makes sense. Okay, yeah, it's a local variable. It's only valid within that function. So lifetime ends in at the closing brace, like I was asking. Okay. So let's call the lifetime body, and then a reference to x produces a reference of type reference to lifetime body for iterate or shorter. You're trying to assign it to this, and that's why it fails. Okay. But okay, I mean that makes sense for that one, but let's go on to this main function here. Create variables to be borrowed below. 4 and 9, create a tuple, borrows, reference of both variables that pass into the function. So printfs is this one. Any input which is borrowed must outlive the borrower. In other words, the lifetime of 4 and 9 must be longer than that of printfs, correct? Yeah. And now we call field borrow. Field borrow contains no references. Yeah, I was gonna also that was my next question. How we pass the lifetime to it. It contains no references to force lifetime A to be longer than the lifetime of the function. But lifetime A is longer because lifetime is never constrained. Or it defaults to static, which means it will be valid for the entire length of our program, right? Okay. interesting. So calling field borrow doesn't pass a lifetime, so it defaults to static how to pass a lifetime to it. You can explicitly pass a lifetime to a function, yeah. Lifetimes are inferred by the compiler at the call site, not passing like type of argument. So when you write field borrow, the compiler doesn't default to, instead it tries to infer some lifetime A that makes the call type checks. Since lifetime A doesn't appear in the function's parameter, there's no constraint tied to anything at the call site. The compiler is free to pick any lifetime, but the function body itself must be valid for all possible choices. That's universal consecution that dooms the borrow. Okay, we can verify this. Tablefish doesn't accept lifetimes. Right. Okay. So you just call it like that. How would you actually make this work? You need to tie lifetime A to something concrete. Typically by giving the function an input or output that uses lifetime A. So we can do something like this. Lifetime A. So by giving it an input like so. Right. Okay. Compiler infers that. All right. Okay, that's clear. Let's go functions. Ignoring elision. Function signatures with lifetime have few constraints. Have few constraints. Any reference must have an annotated lifetime. Yeah, any reference being returned must have the same lifetime as the input or be static. I mean, this is another way of talking about the 3 lifetime edition rules we saw in the book, I guess. Okay, additionally, note that the returning references without input, is banned if it would result in returning references to invalid data. The following example shows of some valid forms of functions with lifetimes. One input reference with lifetime A, which must live at least as long as the function. So you have lifetime A here. You have X, which is a reference to an I32 with lifetime A. Okay. So it must live as long as the function. I mean, that's mutable references are possible with lifetimes as well. So you have the lifetime specifier here, and then you can use that for mutable one. I mean, why would I want a lifetime here when I'm not returning anything? Oh yeah. Okay, well, actually, we are changing the mutable. Yeah, okay, let's use this one. didn't actually say nothing. Okay, so that's what about this one? It's redundant. Okay, so these are just examples. It's okay because it doesn't make sense that they are there. We don't need them. There's no value. Okay, I think we've already seen lifetimes and the rest. So in structs, annotations for lifetimes and structures are similar to functions. We declare the lifetime parameter, and then we have a reference like that. Yeah, and then we can create a single, which is borrowed this, double, reference, and the rest. We've seen this also. You can use it in traits. Well, this is a struct here. Okay. And now you're implementing default for borrowed. And you're doing this like so. Okay. Just like generic types can be bounded, lifetimes themselves can also use bounds. So this means all references in T must outlive lifetime A. The type T must implement trait, and all references in T must outlive A. Lifetime A. So you have a struct ref, and you declare lifetime A. Declare a generic type parameter to that all references must outlive lifetime A here, and then you give it a reference to the type parameter T that has lifetime A. Ref contains a reference to a generic type that has some lifetime A unknown by ref. T is bounded such that any references in T must outlive lifetime A. Additionally, the lifetime of ref must not exceed lifetime A. Okay. A generic function which prints using the debug trait. Yeah. Now you want to print ref. This is just a generic one. And then this is printing ref. A reference to T staking where T implements debug. Okay. And all references in T outlive reference A. In addition, A must outlive the function. After me was outlive the function. Well, this is specific to the print ref function. So you create ref. Oh, yeah, this is the regular print. Yeah, I think that's fine. Question? So you have multiply, declares the lifetime A, has first and second, both have, both are of lifetime A. Okay. Two references and then coerced. Wait, the Rust infers a lifetime that is as short as possible. The two references are then coerced to that lifetime. Yeah. It's going to be the shortest. Yeah, okay. That's already known. Lifetime A. Right. This is another. This reads as lifetime A is at least as long as B. Here we take in an a reference to an iter2 value that has a lifetime of A and return reference that has a lifetime of B as a result of correction. So lifetime A is at least as long as lifetime B and lifetime B. And you have first, you have second, and then you are returning a reference that has a lifetime of B. Okay, well, it's good to know that this is possible, but I think when I need it, I'll move on from it. You have first 2 here. It's longer. This is the shorter. Normally, you do multiply. That's fine. You do choose first. But this is just normal. Why complicate this? Like, this is just normal. You don't need to do this whole stuff here. Nah, I don't know who wrote this. What's this? It's actually from the. Okay, but well, I guess they're just showing it because it's the same thing they have in the Rust book, and they explain it properly in the section on lifetimes. But this is just, I don't know, unnecessary examples. I would say there's no real value in the examples that they have there. Examples are poor. So you have the static lifetime. Yeah, we know about this one. And then static as part of a trait bound. So you have a generic where the generic type, how do you read this again? Is at least as long as the static lifetime. How do you read this? How did I say this? Yep. A generic function that takes value x with the constraint t must satisfy the static lifetime bound. That's not what I asked you. Yeah, okay. References of t must leave at least as long as. Another way to say it is yep. Okay. I think lifetime coercion is not important to what I'm doing here right now. But I've also seen elision. So I think I'm done with this here. Is there something else here? No, we did this already. That's it. Okay. First compiler needs to know how to check whether supplied references are valid. So you can let the programmer know if a reference is at risk of going out of scope before it is used. Remember, references are borrows and do not own their own data. What if their owner goes out of scope? So we should fix the compiler error by updating the function signature. So we have a longest function, like so. Compares and returns either x or y. And it's missing the lifetime specifier. So So we can say let x be ten, let y be 30, and then we can say So the returned value, I mean, the lifetime of result should be the shortest of the lifetimes for these. Yeah. What we're guaranteeing is that, I mean, what the compiler wants to guarantee is that the reference returned from here is valid as long as these guys are still in scope, that they're not dropped before this. That's it. And right now it doesn't know how to do that because, yeah, they're just references. These references can be dropped in the color, so it doesn't know how to do that. So that's the problem. Now we need to tell it how to do that. We can here give a lifetime parameter. We can declare one. Yeah. And then say that x is both x and y have the same lifetime specifier. Yeah. And that yep. And that the value with the reference returned also has that lifetime specifier, and we're good. I mean, there can be the case where we specify it differently. We can actually introduce a second lifetime specifier here. Maybe I should actually do that. And I can give y the second lifetime specifier. And now I'm saying this is a, or rather lifetime a. So he's saying lifetime may not live long enough. Yeah. So what I'm doing is something like, let's say, the two of them have different lifetimes. Right? Something like this. So imagine we have this as the lifetime. No, well, it can't find x in this case. Well, this is not the exact example I want to do, but anyway, we get it. Yeah. So it's really, yeah. Okay, let's just do the next one. So we shouldn't change this function. Fix the compiler error by moving one line. So again here, this is string 1, comes into scope here. String 1, and goes out of scope here. Result comes into scope here, and also goes out of scope here. However, string 2 starts here, and string 2 goes out of scope here. It's dropped here. So, and for this, we're giving one lifetime parameter to this. So yeah, I was saying it's going to be the shortest of the reference to string 1 and reference to string 2, which is this. So it's the shortest will be this one, and we're trying to print result here. That's why we have that problem. So to fix this, we can move that there. Very good. Okay, here. So we fix compile error about the struct. Yeah. So we introduce a lifetime parameter. Okay. And I think that's it, right? We don't lifetime 2, lifetime 3. And we have a test. Oh, it's tests actually. Yeah, so we go to testing now. But I think that's where I'm gonna end it today. It would be cool to continue with testing next. Actually, we're almost done with this thing. Well, we have a few more chapters and we're done. I cannot wait to get back to writing proper code, yeah, after reviewing this. All right, then see you tomorrow or next time. Then, bye.